Good day, everyone. I'm Jessica Lockwood with EA Engineering, Science and Technology. Welcome to our Microsoft Teams live event. I'm going to go over some housekeeping items with you before we get started. Online attendees are in listen-only mode and can ask a question by typing it into the Q&A panel. There is an icon on the top right toolbar that looks like a chat bubble with a question mark inside of it. For this event, Q&A will be open for the entirety of the presentation. However, the presenter will not be taking or responding to questions until the end. Here are Abby Smith and Matt Frigon with today's presentation.
Thanks, Jess. Hi, everyone. Welcome to EA's first webinar on anaerobic digester health and troubleshooting. My name is Abby Smith. I am a project manager with EA for about the past 17 years and also involved in a lot of water and wastewater projects. I'm going to give a little introduction to EA and then turn it over to Matt, our EnviTreat laboratory director. Next slide. So for those of you who may not know a lot about EA, we're a company headquartered in Maryland, 100% employee owned and a public benefit corporation. We have over 550 employees and 25 offices across the US, including Guam and Alaska. We're a full service environmental company ranked consistently high in the ENR. And one of the topics that we're going to talk about today, a unique capability of ours, is our in-house toxicology lab, and then specifically today, our treatability laboratory that Matt will go over. Next slide. A little bit more about EA. We were founded over 47 years ago in kind of the environmental permitting and water natural resource world, but we've really grown to be a full service environmental firm, including engineering, infrastructure, environmental health and safety, technology, and site characterization and remediation. On the water and wastewater side, we really take it from the beginning to the end: planning, evaluation, infrastructure design, asset management, and of course, what we'll talk a little more about today with the operation, maintenance, and monitoring of those programs. Next slide. So to give a little introduction to Dr. Matt Frigon, he has 16 years of experience. He's our director of EnviTreat Laboratories, our treatability laboratory, and really specializes in the design and operation maintenance of all kinds of wastewater treatment for both municipal and industrial customers, including physical, chemical methods, as well as biological. And he'll talk a little bit more about anaerobic digestion today, troubleshooting, and kind of how that monitoring will help. So without further ado, I'll turn it over to Matt.
Okay, thank you, Abby. So yeah, today what we're going to talk about is anaerobic digestion, and specifically monitoring the health of your anaerobic digester, and kind of ways of troubleshooting your digester if things start going unexpectedly. So as part of the agenda, first I'm going to talk about what can be digested, and then determining what kind of materials are suitable for digestion through the BMP, the Biochemical Methane Potential Test. And then about the systematic approach that EnviTreat takes to monitoring the health of the systems as well as diagnosing problems. And then with regard to that, biomass activity, the importance of nutrient composition of the biomass, and problematic materials. So as far as what can be digested, an anaerobic digester is basically a tool for degrading organic compounds. It's not a nutrient removal system for nitrogen and phosphorus, although it does a little bit of that like other systems are. And so what it's degrading is carbohydrates, fats, and proteins generally. But the biomass yield and the biogas yield are dependent on the type of material being digested, and they're kind of inverse of each other. So fats generally have a high biogas yield, but a low biomass yield. Proteins are intermediate, and carbohydrates have a low biogas yield, but a higher biomass yield per gram degraded. And to put that into terms of kind of normal everyday items that we might know about, fats, oils, and grease, of course, are fats, and they have high biogas yield. Grass clippings and fruits and manure are on the intermediate side of biogas yield, and then yard waste, straw, paper, and things like that are low biogas yield items. So the first thing you want to do after you have an organic that you want to degrade is you want to see if it's suitable for digestion anaerobically. Many things aren't. And so to do that, there's a test called a BMP, a biochemical methane potential test, that is commonly done. There are a lot of standard methods. OECD has a standard method, EPA, ASTM, they have standard methods, and VDI is a German method. And what these do is they determine whether the material can be biodegraded, and then the quality of biogas, quality and quantity of the biogas that comes out of the degradation. And biogas is really important because it has value as an energy source. So if that can be collected and maybe processed in some way and then burned, you can get energy. So these methods all generally rely on taking a serum bottle, adding a portion of the organic you want to degrade, either as a VSS or as a COD, then adding some biomass and allowing this to incubate for 28 to 30 days. At the end of that time, they measure how much biogas, or as it's going on even, they measure how much biogas is produced, and then analyze the biogas and its different components, basically methane, carbon dioxide, and hydrogen sulfide. So the graph that's there on the right is an example of an EnviTreat typical BMP. And that's hooked up to a respirometer so we can see how much biogas is being produced on a minute-to-minute basis. But generally, EnviTreat, unless requested, doesn't use that method for performing a BMP. EnviTreat has developed its own method, or our own method, for doing BMPs. And for the reason is that it's faster, it can be done in 10 days, and it produces more information than the typical BMPs from the other the typical ones, OECD and EPA ones and things like that. So we call it the high rate BMP test, and it tells you the same things as the regular BMP test. First of all, the volume of gas produced per gram of chemical oxygen demand degraded, the composition of the biogas, the measure of biodegradability of the material. But it also can tell you whether the material is acutely toxic, and this BMP test is the same test we would use to determine acute toxicity of a wastewater, and it will also give you a rough idea of the appropriate solids retention time to use in your anaerobic digester. And so examples of this are on the right there. On the top is a BMP. For these BMPs, we typically have a control reactor and then a 20 and 30 and 45-day SRT, that's solids retention time reactors, and we run them all simultaneously. They're all hooked up to a respirometer so we can see how much biogas is produced and how fast it's being produced. And so as you can see in that top right graph, the pink line is the 20-day SRT. It started going up on the first feeding, but on the second feeding, the second day, it dropped to nothing. And basically that reactor was not viable after that point. The 30-day SRT reactor, the green line, it went out to about 3 days and then failed. And the 45-day SRT reactor went out to about 5 days and then failed. So this information, this failure during the BMP test is something that you wouldn't see in the other BMP tests, because they would just have one feeding, it would keep going, it would give you a measure of biodegradability. But the reason that our BMP test is a little bit different is that there's subsequent doses. So when the initial dose is added, it's added in such small proportion compared to the volume of the reactor that it's just diluted and there's no toxicity. But acute toxicity develops as several doses are added over the course of 10 days. The other thing that the EnviTreat BMP test does is it allows you to compare the different SRTs. So the bottom right graph there, you can see that the difference between the 20, 30, and 45-day SRTs, the 20 is the red, the 45 days the purple, and the 20-day SRT is getting about 85% efficiency on its methane production per gram of COD removed. The 45 days getting about 95% efficiency. So looking at that, depending on what you want to do with your reactor, you might want to choose one SRT over another, and that's information that only comes out of the high rate BMP test. When talking about digester operation, we have a kind of a set systematic approach for how we go about doing that evaluation. So I'm going to talk about that just for a second now. There's a lot of words on this slide. I'll just go to this workflow here. So the first thing we do is ask if the system's performing as expected. If it is performing as expected, we do routine monthly checkups, and we do these for several clients monthly right now. We also do quarterly for other clients that want to do it a little bit less often. But during those checkups, we check the biomass activity, the biomass nutrient and mineral composition, the volatility of the biomass, and if it's a granular reactor, the granule size and shape. If it's not performing as expected, the first thing we ask is, what's changed? Is the wastewater changed? Have you changed the chemicals in the upstream process? What's changed in what's going into the reactor? If nothing's changed, we go through basically the same routine monthly checkup procedure, except that we add in, we also check the VFAs of the mixed liquor, the volatile fatty acids. And we also perform a diagnostic model of the process to determine if the loading rate or the solids retention time is inappropriate for that reactor. If all that appears to be okay, then we'll perform a toxicity BMP, which is similar to what we just talked about, to determine if it's the wastewater itself that's toxic. If there is a problem, if there is some new chemical or something has changed about the wastewater process, or wastewater that's going into the process, we'll perform a chemical use survey, and that basically analyzes these different new chemicals and determines whether the mass loading on the reactor could be problematic. And then from that, we work with the client to determine, or with the operator to determine if they can change the chemical that's being used, use less of it, and we also check the biomass activity to make sure that the biomass isn't killed. So these are kind of our procedures for going through, checking the health of the reactor and seeing if something goes wrong, determining what that problem is. So I'm going to go through each one of these different steps individually and kind of explain how we do them and what the procedure looks like. So for biomass activity, that's one of our most important tests because activity of the biomass is crucial to the operation of the digester. The active biomass that's in the digester is the thing that's actually doing the work, the thing that's turning the organics into methane. So if there's low activity, that means that that there's not a lot of organisms to do the work that you need them to do. A lot of operators associate VSS with activity, but in fact, the active biomass in the VSS is very low. If we have an activity of 25%, that's great. If the activity is below 15%, that's when we start considering it to be a problem. And the real problem is because even though you think that you've got a lot of VSS, a lot of organisms to do the work, so you're loading the reactor in a certain way, the less and less organisms you have, the higher and higher those organisms are loaded. And as you'll see later on, for an anaerobic system, if they're very highly loaded with organics, they can easily sour the reactor because the methanogens can't remove the organics as fast as they're produced. So example of biomass activity tests is a failed one is on the bottom left there. That was a brewery. So basically they gave us a sample and we tested the biomass activity, and you can see that there was no methane production over the course of 4 days. So that biomass was pretty much dead, even though they thought that it might be alive because they had just reseeded it earlier that month. On the bottom right there, those graphs are a typical activity test that we have. On the top is the cumulative methane production curves. On the bottom are the rate curves. From that, we can see that there's good methane conversion of the organics to methane because about 395 milliliters per gram of COD is ideal. So those curves are looking good. They're right at about 400 there. And then the bottom, the methane activity is about 0.47 grams. And that's a pretty good activity. And specifically for this reactor, since we've been doing this reactor every month for the last 10 years, it gives us a good track record of how that reactor is behaving. So if we see it going from month to month, staying the same, that's good. We know nothing's bad's happening. But if we see it declining, then we can know that something probably as bad is happening to the reactor, and we're going to have to do something with operation to fix that. So activity test is a really valuable test, and it takes 1 day to do it, or a couple days, I'm sorry, because it's 4 feedings, but one feeding per day for 4 days, and you get a really good sense of how much of your biomass is active. The second test that we do, basically whether the reactor is healthy or not, is the nutrient composition of the biomass. We want to know both the macro and micronutrients, macronutrients being nitrogen and phosphorus, and micronutrients being minerals. Nitrogen and phosphorus, if they're low, that means that the biomass can't grow as it would like to. So basically, you're not producing as much biomass as you potentially could, and that's a problem because the methanogens grow so slowly that you really need to be producing more biomass constantly to replace the what's being wasted. The micronutrients are really important because they're essential for enzymatic reactions that the biomass for the methanogens to do their work, and especially important are iron, cobalt, sulfur, and zinc. So on the right there is kind of a typical analysis that we would do. We'd go through, because of just basically 15 years of experience with these biomasses, we know what the typical composition of the biomass should be. So in this analysis, we found that zinc, boron, and selenium were low and might be deficient, and then the cobalt was deficient. And cobalts are one that's often deficient, and it's a really important one for enzymatic reactions. Now, from this analysis, we also might identify things that are too high, like any of those metals, copper, zinc, nickel, they could be too high, which might be toxic to the system, or calcium might be high, which might we might have concerns with scaling in the reactor. The next thing that we look at if it's a granular system is the granules themselves. We put the granules through a sieve and sieve out the basically the granules below 0.5 millimeters. The ones that are above 0.5 millimeters, we also put them through sieves and put them into different categories, and then we put them under a microscope and look at them. The granules on the bottom right there look good. Granules should be rounded and nice and smooth. They should be consistent. They shouldn't be fractured, and they should be black in color. And those ones on the bottom right there look really good. The ones on the top right, they don't look so good. They're kind of rough surfaces, uneven. They look a little bit broken. They're white, which indicates a mineral deficiency, probably iron. And so just by looking at the granules, you can get a good idea of the health of the granular system. So how do the granular systems why do they have problems? One is from toxic impacts from solvents such as methylene, chloride, BTEX, and isopropyl alcohol. They can start to fracture due to too many monovalent cations such as sodium and potassium. Sodium's a particularly problematic one or we see it often because it's being used with caustic upstream for various sanitization and cleaning and things like that inside the plant. Ideally, we'd want the monovalent to divalent cation ratio to be less than 1:1. Another thing that we want to look for is also precipitates, because these can cause the granules to have excessively high density. And what that means is that they can't be suspended properly in these suspended growth systems, and that gives them problems. So one of the last things that we like to do for healthy systems, but we also do it when diagnosing systems that are having problems, is process modeling. And that process just generally is working with the operators to find out data about their process, what their influent wastewater characteristics are, what their SRT is, what their HRT is, and the system mixed liquor, volatile, suspended solids, and mixed liquor, suspended solids concentration. We then compare that to what we'd expect from mathematical modeling of the system, and from that analysis, we can often identify problems. So the modeling, in conjunction with the monthly activity testing and nutrient monitoring, really ensures that your system has a healthy biomass and allows you to catch the system if problems arrive, from observing activity starting to fall, nutrient deficiencies, or model not agreeing with operational characteristics provided from the field. So one of the operational issues that we identify a lot as a problem is SRT. SRT is a really important design parameter for any biological system, but it's especially important for anaerobic systems. That's because if the SRT is too low, it can lead to incomplete degradation of waste organics. That is, the organic comes in and the biomass doesn't have enough time to degrade it, so it flows out with the effluent and leads to poor efficiency of waste removal. The other thing it can lead to is washout of biomass, and most importantly, it can lead to overloading of biomass. And what that means is when the organics come into the reactor, the acetogens break them down into VFAs, which then cause the system to sour and kill the methanogens. And I'm going to talk a little bit about that more in a second. So to determine an appropriate SRT for a reactor, we typically do something called a treatability test. The treatability test is very similar to a BMP test, except it's run out to 45 days. And so a typical treatability test you can see is on the right there. At 10 days, all the SRTs look pretty good. They're all generating about the same amount of methane, which and being the reactions completed in 24 hours. But on the 11th day, so there's no acute toxicity that we noticed there. But on the 11th day, the green line, which is the 20-day SRT, it starts dropping off. And basically by day 18, that reactor has failed. The 30-day reactor, which is the blue line, continues along and is pretty good until about day 28, and then it starts having suboptimal performance as well. While the 45-day reactor, which is the red line, continues to have consistent performance all throughout the 45 days of the treatability test. So for this example, we would say that we would not recommend running this reactor at anything less than a 45-day SRT. And you wouldn't know that unless you did this treatability test out to the 45 days. So they're really important for determining, for properly designing and operating your system. Generally, longer SRTs have better treatment efficiencies. They're more robust to shock loads and toxicity, and they reduce waste sludge production. So, why wouldn't you just run your SRT at the longest you could all the time? And the reason is it's a solids handling issue and how many solids you can retain within the reactor without blowing them out, or if you're using a filter, how much solids the filter can handle. So now I want to talk a little bit about problematic materials. First, I want to talk about surfactants and disinfectants. So surfactants, of course, have three kinds: cationic, anionic, and non-ionic. The most concerning of these are the cationic surfactants because they include the quaternary ammonium compounds, which are also called quats or quaternary amines. These inhibit metabolism and they interfere with cell permeability. And the real issue with them is that once they get into the reactor, they adsorb to the surface of the biomass, and you can't get them out of they don't flush out of the system with the influent and effluent wastewater. The only way to get them out is to waste biomass, or in really hard cases to just dump all the biomass out of the reactor and reseed it. The next kind of surfactants are non-ionic surfactants. We don't see those very much, but they can cause problems with the cell membrane. And then there are anionic surfactants, and they cause problems with the cell membrane. The most common one we see of these, and the most toxic, is the dodecylbenzene sulfonates. Now, there's a couple other groups, the alkylamines and ethers. They are also toxic, but they're toxic to a lesser extent than the dodecylbenzene sulfonates or the quaternary ammonium compounds. And it's also, depending on chemical to chemical, they vary on their toxicity. So really the only way to determine how toxic a certain product is to test it with a toxicity test. And that's a little bit different from a BMP, but I'm not going to go over that here. The last disinfectant that I want to talk about is called peracetic or peroxyacetic acid, PAA. And this is a very common disinfectant used in many cleaning products. It's especially it's problematic for aerobic systems, but it's especially problematic for anaerobic systems because it doesn't break down very quickly in the anaerobic systems. and it is toxic in much lower concentrations. I've fed PAA to an aerobic system at 50 milligrams per liter, and it was able to chew it up. Our typical limit in an anaerobic system is 0.5 milligrams per liter. So the anaerobic biomass is very sensitive to the PAA. So when we have these problematic materials, we want to do this chemical use survey to figure out if it's going to have an effect on our digester or not. And so what we'll typically do is work with the operators and the upstream producers or users of these chemicals. And this could even be a municipal plant. We've done it before where we've gone to all the industrial dischargers into a municipal plant and gotten all their SDSs. And we go through each of the chemicals and break them down into their different components. And based on the gallons of usage per day, we come up with a mass loading on the treatment plant. And so in this example, the PAA is, you can see there's 0.567 milligrams per liter per day, which is above our threshold of 0.5 milligrams per liter a day. So we would expect some toxicity out of that. And also the dodecyl benzene sulfonate is also 5.4, which is above the threshold of 5.0 milligrams per liter per day. So we'd expect some toxicity from that. We also notice that there's hypochlorite and alkylamine oxides and peroxide in the chemical formulations that they're using, although not at toxic levels, but we'd still want to note that because if something changed in the future, we would, it might be that they increase the usage of one of these products and that those then become a problem in the future. And so it's really important to do one of these chemical use surveys because things like PAA and peroxide and even some of the others, if you try to test for them in the reactor, you get a very inaccurate reading. The PAA, you won't be able to see at all. Peroxide probably won't be able to see at all. Some of the other ones, you'll get erroneous readings. And so the only way to be sure and to really absolutely know what kind of loading you've got on your reactors to do a chemical use survey like this. Here's some other problematic organics and their concentrations. The ones we run into the most commonly out of these are the long chain fatty acids and the tannins. The tannins, because we do a lot of work with pulp and paper, and so they of course have tannins in because they're working with paper or wood products, and then also with landfill leachate, they often have problems with high tannins. So other problematic materials, ammonia and sulfur, these are necessary for the biomass to live. Both of them are toxic in their non-ionic form, and it's closely related to pH. With ammonia, it's a little bit more complicated because it's related to pH and temperature. For the sulfate, so for the sulfide, H2S is the toxic form of sulfur, and so we look for how much sulfate is going into the reactor. And we want the sulfate to be less than 5% or at most less than 10%. All that sulfate gets converted into hydrogen sulfide, and it's toxic to methane formers, and it can also create odor problems. So you can see on the bottom right there, the graph, the lower the pH, the more H2S form of hydrogen sulfide you have, and the more toxicity you have. So you want to keep the pH higher for hydrogen sulfide. But for ammonia, the toxic concentration is about anything greater than 1,500 milligrams per liter. We've run them higher than that, but that's just a general rule. And we measure the TKN, which is a combination of both the organics and the ammonia that's going into the system, because any of the organics will break down into ammonia eventually. And as you can see in the top graph there, for ammonia, the higher the pH and the higher the temperature, the more toxic it becomes. So generally for our reactors in the lab, we like to run them at a pH of 7.2 because that minimizes the toxicity. It's kind of like a good middle ground between both species of ammonia and hydrogen sulfide. Fatty acids are also a problem, and it's kind of a weird problem because the way that the anaerobic digesters work is they take complex organics, turn them into volatile fatty acids, and then turn those into to methane. But if there are too many volatile fatty acids in the reactor, that in itself is toxic to the organisms. And again, we're concerned with the unionized form of the volatile fatty acids, and they're more toxic at lower pH because more of the unionized or non-ionized form exists at the lower pHs. Now, these volatile fatty acids build up generally because there's not enough methanogens to convert them into methane. So the acetogens, they're quicker growers, and they're cranking away, eating the organics and breaking them down to volatile fatty acids, and the methanogens just can't keep up with them. So this buildup of volatile fatty acids is especially problematic during startup of the reactor, or when the reactor, something's changed in the way the reactor is being fed and it's still stabilizing. That's because, as I said, the methanogens are still, the population is still developing, and so at the beginning of the reactor operation, you want to be really careful and start up slowly and make sure that you're getting rid of all the volatile fatty acids that you're producing. And so we look at the profile of the volatile fatty acids that we see in the reactor, and we generally test for acetic acid, propionic acid, butyric acid, isovaleric, and normal valeric acid. If we look at these, they give us a window into what's going on in terms of the biology inside the system. If we see a buildup of acetic acid, that generally means there's an overloaded situation. That means the organics that are going into the system are more than the are converted into VFAs faster than the methanogens can remove them. If we see a buildup of propionic acid or the other VFAs, and that generally points to some kind of toxicity issue. The reason for that is the butyric acid, isovaleric, and normal valeric acid, those are only produced when the normal biological pathways that lead to propionic acid and acetic acid can't be followed for some reason. There's some inhibitory or something that's causing the endpoint to end in those VFAs instead of propionic or acetic acid. So we monitor for those, and that's we would recommend doing that at least monthly on a full-scale reactor. In the lab, we test at least weekly, and if we have a problem, we would test even daily for these VFAs. The last thing I want to talk about is filamentous growth. It's not a very common problem, or I should say filamentous growth and foaming. It's not a very common problem in anaerobic reactors, but it can be a problem, and we've had recent projects where this was a problem. It can be a problem or formed either from filamentous bacteria. It can also be formed from whatever the feed waste is that's going into the reactor. If it's from filamentous bacteria, that's generally from a high carbohydrate feed waste. The filamentous bacteria form, and then they interact with the biogas also being formed in the reactor, and they foam. Foaming can also occur due to surfactants in the feed wastewater, high protein content, and then shock loading of the reactor. So on the right there, there's some pictures of some foaming reactors, although those are aerobic reactors because I didn't have a camera to get into an anaerobic digester, and because those are mostly sealed off. So that's pretty much my presentation, and if you have any questions, I'd love to take them.
All right, Matt, we have some questions online. Let's start at the beginning. The first question here is, what type of systems is the EnviTreat analysis best suited for in terms of size or generator type?
I would say that the analysis that we do are across all kinds of systems. We do granular systems, high rate systems, low rate systems, and anaerobic lagoons. So the analyses that we do are pretty broadly applied to all anaerobic systems.
All right, the next question here is, does a high solvent COD loading impact granular sludge growth, or is it just a question, I'm going to mess this word up, of acclimatization?
Yeah. No, I mean, so that's a good question. It will mess up the granules, as you say, or cause more fracturing of the granules, but there can be some acclimatization. We have one paper mill that we don't know why the granules always come in fractured and looking really bad, but the activity is always really but the activity is always really good, and so it seems to have acclimated to whatever's causing the fracturing in the system. It's possible, but I think that would depend on the specific wastewater and whether the biomass could be acclimated.
All right. The next question is, how does the EnviTreat BMP test differ from the traditional BMP test? And then a follow-up question of which test is most suited for determining working biomass in your reactor?
Well, so the EnviTreat BMP test differs because the main difference is that the regular BMP test is just one dose, and then it waits till the full degradation for 30 days. The EnviTreat BMP tests doses every day for 10 days, and so because of that, it acts more like a actual reactor than just a theoretical test, and so you can derive a lot more information out of the EnviTreat test than you can from the traditional BMP test. Specifically, if there's acute toxicity, I mean, above and beyond what the regular BMP test does, if there's acute toxicity and what kind of SRT is appropriate for treating the waste. As for the second question, the BMP test is related to the wastewater that's being fed to the reactor, so it's about the wastewater. The activity of the microorganisms that are in those BMP tests is just from whatever reactor they came from, so it doesn't really relate to that. The activity test is the test that would where we would feed it some acetate. We would take some biomass from some reactor or a lagoon or whatever, and then basically centrifuge it out and add some acetate to it. That would determine the activity of that particular biomass in that particular reactor. So they're kind of two different analyses.
All right. Another question here is, did you notice that alkalinity may be a bigger factor than pH? I had a reactor running in the 7.2, 7.4 range that wasn't performing and ultimately did much better with magox treatment.
Alkalinity is, one of the really most important parameters in operating an anaerobic system, and it is highly related to pH. So generally we want 2,500 milligram per liter bicarbonate alkalinity, and it's very important that that you're measuring bicarbonate alkalinity, because the volatile fatty acids that are in your reactor will also be measured as alkalinity, so I guess to answer that question is yes, you need to make sure you have enough alkalinity, and also that your pH is in a good range to maintain that alkalinity. The lower your pH, the more you're going to drive the bicarbonate into carbon dioxide. The magox, I'm not sure if I've used that product, but certainly in the lab, if we see pH problems, our first thing to do is add bicarbonate. You can basically overload the thing with bicarbonate, and it'll just, whatever it doesn't need, it just turns into CO2, and it'll give you enough alkalinity to operate your reactor.
All right. I have another question. Why is doing a chemical use survey a more effective method of determining potential toxicity to your digester than simply testing for suspected chemicals in the mixed liquor?
Because a lot of the chemicals you can't measure in the mixed liquor because they just disappear and you get erroneous readings, or maybe you take sample from one portion of the reactor and it's different from another portion of the reactor. But if you do the chemical use survey, you're absolutely sure what kind of loading of each chemical you're having on the plant, and it takes away any of the guesswork of the analyses that may, the analyses may fail, or the method may not be right, or the sample may not be right. But it takes away all the guesswork for the analyzing the sample out of the mixed liquor.
All right, I have a few more questions here. What is recommended test for VFAs? Is titration method with acid or spectrometer test more appropriate?
Well, you can do it a couple different ways. In fact, I just sent a protocol to one of the companies that we work for yesterday for how they can just do it in their lab. Basically it's titration, but all they have is a pH probe. And they basically just add acid until they hit certain set points, and I gave them some equations so they can work out how much their VFA and their VFA alkalinity compared to their total alkalinity. Basically, you titrate the mixed liquor so to a certain point, and that a portion of that is VFAs and a portion of that is a bicarbonate alkalinity. So it can be as simple as a pH probe, which kind of gives you a holistic overview of what the VFAs are in your reactor. In our lab, we use a GC, and that way we can, see all the different acetic, propionic, butyric, and all the other VFAs very specifically. And we like that method because then you can see, if the loading is too high or if there's toxicity issues and things like that. And the test is very quick. It only, we only need about a 50 milliliter sample, and we can do it in less than an hour. So it's a really useful tool to have. But you can go as simple as just a pH probe.
All right. You noted issues causing excessive VFA formation. Is there an issue if VFA concentrations from digester draws are regularly low, for example, less than 10 milligrams per liter?
No, if they're really low, that's great. The reactor is performing well.
All right. Have you seen in your testing impacts from all of the additional cleaning and the associated chemicals that are being used because of COVID-19?
No, I haven't. No, because in our lab we generally get samples, from the manufacturing process. They don't. They don't really have to do anything with the COVID-19, unless you're saying that. If you're asking, are we doing less testing because of COVID-19? Is that the question?
I think the question was more related to have the chemicals and additional cleaning and things like that have been associated with COVID-19 causing additional. Yeah,
no, I don't know. No, I haven't. That's a good question. I haven't noticed anything like that yet. But yeah, it's a good question. In fact, that makes me think there's a brewery that we've been working with that's having a lot of problems recently, and one of the things we've been trying to figure out is if they're using more disinfectants upstream. That may be because of COVID-19. That's a good question.
All right. Can you comment on performing alkalinity testing in conjunction with VFA tests? Operators have traditionally used ALK-VFA ratios to monitor digester health.
Yeah, that's kind of what I was describing before. You basically can use a pH probe and some acid. You basically acidify your wastewater down to a certain point, and that is your VFAs. And then you acidify it more down to another point, 4.3, pH 4.3, and then the amount of acid you use for those two to reach those 2 points, you can then do a calculation to figure out what your bicarbonate alkalinity is, your total alkalinity, and your VFA alkalinity. So yeah, there's a procedure for doing that. Like I said, I just sent it to somebody yesterday, and it's just done with a pH probe.
All right, the last question we have online is if toxic situation exhibits in a reactor, can the reactor be flushed with water and restarted rather than reseeding, or would this shock the system?
Well, the problem with that is that generally the methanogens are all dead. So you could potentially just decant everything and fill it up with clean water. But in order to develop enough methanogens to be a viable biomass, it might take 6 months. So you could do that, but most people don't want to wait around that long to get their reactor up and going again. So.
Well, thanks, Matt. Those are all the questions I had online.
All right, cool. Well, thanks a lot for attending, and have a good day, everybody.
Thanks, Matt. You too.